In this next example, we have to find all the real numbers theta for which this complex number is entirely real. That means its imaginary part is 0. So we start the solution and immediately we start manipulating this complex number. Our aim here is to express it in this standard form, that is real part plus I times imaginary part. To do that, you already know what to do. You have to make the denominator real. Originally it's 1 minus 2 by sine theta, so you multiply and divide by its complex conjugate, which is 1 plus 2 by sine theta. And then you perform the multiplication in the numerator. 3 times 1 is 3, 3 times 2 by sine theta is 6i sine theta, 2i sine theta times 1 is 2i sine theta, and 2i sine theta times 2i sine theta is 4i square sine square theta. And the denominator is in the form a minus b times a plus b, so it will be a squared minus b squared. So that way we get this 1 squared minus 4i square sine square theta. Now this I squared is minus 1, so 3 minus 4 sine square theta. So that is without I. And the terms having I are 6i sine theta and 2i sine theta. So together they give us 8i sine theta. And the denominator becomes 1 plus 4 sine square theta, because I square is minus 1, that minus and this minus will give us plus. Note one more thing, that this denominator is not equal to 0. I mean, it cannot possibly be 0, which is actually what we want here, because we do not ever want any denominator to be 0. And why is it not possible for it to be 0? That is because this is 0 if and only if sine square theta is minus 1 divided by 4, and that's not possible because sine square theta is a square, so that cannot be negative. But the important thing here is that this is a real number. It does not involve any I. So then we divide this by this, obtaining the real part. Okay, so this is the real part of our complex number, and we divide this by this. So this is the imaginary part, 8 sine theta divided by 1 plus 4 sine square theta. Now for this complex number to be entirely real, the imaginary part has to be 0. That's a necessary and sufficient condition. And from that condition, we are going to say what theta can possibly be. So the given complex number is entirely real if and only if this imaginary part is equal to 0. 8 sine theta divided by 1 plus 4 sine square theta has to be equal to 0. If and only if means what? It means that if this is 0, then this is real, and conversely, if this is real, then this is 0. And this quantity is 0 if and only if. So again, we did not write if and only if, we are writing it slightly differently, but with the same meaning. The above equation means this equation is equivalent to this condition, that sine theta is equal to 0. This ratio being 0 has nothing to do with the denominator. It entirely depends on the numerator, and 8 of course is not 0. So the only way this can be 0 is sine theta being 0. And you know very well from trigonometry precisely when sine theta is 0, namely at these values of theta. That is precisely when theta equals an integer multiple of pi. Theta is of the form n pi, where n is an integer. So for these values and these values only, this complex number will be entirely real. And there is one more example. And that remaining example is this. We have to convert this complex number into polar form. So let's do that. So we first bring our complex number into the standard form by doing the necessary stuff. So first, of course, you just write what these values are. The angle involved is pi over 3 radians. So cos pi over 3 radian is 1 over 2 and sin pi over 3 is square root of 3 divided by 2. And then of course this 2 will go to the numerator and the denominator is 1 plus I root 3. So next we would like to make the denominator a real number. So we multiply and divide by its conjugate. And then if you continue the calculation, what are you going to get here? I times 1 is I of course, minus I square times root 3 minus 1 plus I root 3. And the denominator becomes a square minus b square. So 1 squared minus I square times root 3 squared is 3. And we are intentionally leaving this 2 outside because of this. I mean, ultimately the denominator becomes 4, so you can then cancel 2. And the numerator now becomes what? If we collect the real numbers from here, you see this I square and minus would give us plus because I square is minus 1. So that way we get root 3 and here we have minus 1. And I root 3 give you root 3 plus 1 times I. So that means finally the number takes this form. Square root of 3 minus 1 divided by 2 plus square root of 3 plus 1 divided by 2 times I. So this is your real part and this is your imaginary part. Alright. So now what shall we do? We will now assume that say r is the modulus of the complex number and theta is an argument. And then we would find r and theta, and using them we can write the polar form of course. So let r be the modulus and theta be an argument of z. Don't write let theta be the argument because a complex number has infinitely many arguments and theta is one of them, any one. Then we know these relations. R cos theta is the real part and r sin theta is the imaginary part, and again I am repeating, I is not a part of the imaginary part. The imaginary part of a complex number by definition is itself a real number. Okay, the moment you say imaginary, there is a tendency of putting I with it. Don't do that. Okay, so now we have these two equations. From them, finding r is very easy. You square both the equations and add them. So the left hand side would become r square times sin square theta plus cos square theta. So that's why it is r square. And the right hand side of course is this. Now I am not going to go through this very simple calculation. You can do it yourself. I mean, you can already see what we did. We expanded the squares, and after simplifying everything, we are getting 4. So that means r is 2. Actually, you get plus 2 or minus 2, but because your modulus has to be positive, so that is why r is 2. Positive means in general it's not negative. Here it is positive, and hence now you can use this value of r back in those equations, and then you will see how you can find theta. There has been a mistake in calculating that value of r. Actually, r square is not 4. I forgot that there was this 4, that means 2 square in the denominator. Okay, so whatever I did there, it's not correct. R square would be equal to 2, so r would be square root of 2. And when you use that value back in those equations, you get these two equations. That is, you get square root of 2 times cos theta equals root 3 minus 1 divided by 2, and then you bring that square root of 2 over to this side. Similarly, you get sin theta equal to this. Now you note that you can break this down like this. So what you do, first you write square root of 3 divided by 2. So write that as one ratio and then multiply it by 1 over root 2, that is the other ratio. Similarly, that other term would be written like this, 1 over 2 times 1 over square root of 2. Now note that root 3 over 2 is cos pi divided by 6 and 1 over root 2 is cos pi over 4. Similarly, sine of pi over 6 is 1 over 2 and sine of pi over 4 is also 1 over root 2. So now you recognize this form cos A cos B minus sin A sin B. That is the cosine of A plus B. And this turns out to be 5 pi over 12. But only this is not enough. I mean, if you take the value of theta as 5 pi over 12, one value of theta, then you also need to verify that that also works for this second equation. So I simply wrote sine of 5 pi over 12 is also similarly this. But how? So you have to verify this part. What will you do? You do a kind of back calculation. That is, you start from here and then you go to the value. The only difference is that in place of cos you would be having sine, and then you use the angle sum formula for sine. Sine A plus B is sine A cos B plus cos A sin B. That way you will be able to get this. Note one more thing, that the angle sum formula for sine involves plus in the middle, and that's how you actually also have a plus in the middle here. So anyway, so you do that and you will get this value. And that is why you can take 5 pi over 12 as one value of theta. Not that you have to take this value. Any other value would also work. Because this equation cos theta equal to cos 5 pi over 12, if you write its general solution, you are going to get infinitely many thetas. But we need only one. So in this case, we are not trying to find all arguments, but just one argument. And that too, the principal argument is not necessary here. Any argument works. So then you can write the polar form of z like this: modulus times cosine of argument plus I times sine of argument. Do not use another value of theta here, okay? When you write polar form, you have to use the same theta in both the places. And with this, all the miscellaneous examples are over. So next we can start the miscellaneous exercises, which is what we are going to do next week. So see you next week with this. Until then, this is me, Lucifer, from A Mathematical Room. Have a nice day.